Well, on the surface, incredibly simple. What is the mass of an electron?
Mm-hmm.
You'd think that's a fundamental constant of the universe, right?
You would think so.
But here's where it gets really interesting. Within the unique environment of a crystalline solid, that very fundamental constant can appear profoundly, even dramatically different.
It's a fantastic example, really, of how context can redefine even seemingly intrinsic properties. Our deep dive today is all about how the quantized vibrations of a crystal lattice, what physicists call phonons, profoundly affect an electron's mass,
Okay.
leading to a phenomenon known as mass renormalization.
Absolutely. Our mission, then, is to unpack how this dynamic interaction literally dresses the electron, creating a new, heavier quasiparticle we call the polaron.
Right, the Polaron.
We'll explore how we know this isn't just theory, that it's physically real and measurable, and then reveal its surprising, far-reaching consequences for everything from how well a material conducts electricity
Yeah, basic conductivity.
to the almost magical phenomenon of superconductivity. So let's unpack this.
Let's do it.
To really grasp how phonons add weight to an electron, we first need to set the stage a bit.
Okay.
When we talk about electrons in a solid, we're quickly entering the realm of quasiparticles.
Mm-hmm.
These aren't just isolated particles, they're sort of emergent entities whose properties are fundamentally defined by their interactions with the crystal around them.
That's right. Imagine the simplest model first. An electron in a perfectly ordered but rigid crystal lattice.
Oh.
Static.
Okay, rigid lattice.
Its wave-like nature means it interacts coherently with the entire lattice. So this isn't a free electron in a vacuum. It's what we call a Bloch electron.
The Bloch electron.
And even at this stage, its mass is already modified. This modified mass is the band effective mass, or M star.
So if I'm picturing this right, this M is a brilliant simplification, isn't it?
It is, yeah.
It lets us treat that Bloch electron as if it were a free particle, but with a modified mass that accounts for its complex dance with the static, rigid lattice.
Exactly.
And I recall a key detail here. M isn't a fixed constant. It's actually inversely proportional to the curvature of the energy band.
That's the key.
So a sharply curved band means a small, mammy, highly mobile electron. But a flat band implies a large, even infinite Ma, meaning a localized, sluggish electron. Is that about right?
Precisely. And what's crucial to grasp here is that this band effective mass represents the first dressing of the electron.
The first layer of clothing.
Exactly. It's the bare particle in our solid-state system before we even introduce the dynamic, vibrating nature of the crystal.
Right, because real crystals aren't static.
Not at all. Their atoms are constantly vibrating about their equilibrium positions. And these aren't random jiggles, mind you. They're coordinated collective oscillations that propagate as waves.
And just like light waves are quantized into photons, these vibrational energy packets are quantized into phonons.
Phonons, yeah. So we've got these bosonic quasiparticles possessing defined energy and crystal momentum.
Okay.
And we typically distinguish between two main types. Acoustic phonons,
Like sound waves.
where adjacent atoms move in phase, yeah, much like sound waves, and optical phonons,
Okay, optical.
where atoms in multi-atom unit cells move out of phase. Now, in ionic crystals, these optical phonons create oscillating electric dipole moments.
And I understand those are absolutely key to the strong interaction we're talking about.
They really are.
So we've got this electron, already a Bloch electron, and now these vibrant, energetic phonons. How do they actually, dance together?
That's exactly the right question. And to understand that dance, we can draw a powerful analogy from quantum field theory, QFT.
Okay, QFT, how does that help?
Well, in QFT, a particle's bare mass is theoretical, something we can't directly measure. What we actually observe is the dressed mass,
Dressed mass.
which includes the effects of its self-interaction with surrounding quantum fields, like an electron constantly emitting and reabsorbing virtual photons. It effectively dresses itself.
Okay, I see the analogy. So this helps clarify the hierarchy in condensed matter. Step one is the fundamental electron in a vacuum.
Right.
Then its interaction with the static crystal potential gives it its first dressing, becoming a Bloch electron with its band effective mass. That's the initial layer of clothing.
Perfect. And then the second renormalization occurs. The lattice is no longer static, it's dynamic, alive with phonons.
The vibrations kick in.
Right. The Bloch electron interacts with these phonons via what's called Electron-Phonon coupling, EPC.
EPC, okay.
This interaction then dresses the Bloch electron further, wrapping it in a cloud of virtual phonons, creating our new quasiparticle, the polaron.
Ah, the Polaron. So the Polaron mass, impole, is fundamentally a renormalized version of the band mass. Okay, impole M plus some added mass from the phonons.
Exactly. Bumph, the phonon contribution.
It truly is like phonons are adding a second, maybe heavier layer of clothing to an already dressed quasiparticle. Sounds like a pretty big deal.
Oh, it is a huge deal. The heart of this phenomenon is that electron-phonon coupling, EPC. Fundamentally, it arises from the electrostatic forces, the Coulomb forces, between a charge carrier electron or hole and the charged ions that make up the crystal lattice.
Right. I can kind of picture it in two ways. Either the electron is moving, its electric field displaces ions, and boom, creates a phonon, essentially transferring energy and momentum to the lattice.
Yep, that's one way.
Or, conversely, maybe a pre-existing phonon creates a local, time-varying distortion, generating an oscillating electric field that then scatters the electron. It's a give and take, right? A constant interaction.
Exactly, it works both ways. And while various phonons can interact in polar materials, think ionic crystals, polar semiconductors like gallium arsenide, or these interesting metal halide perovskites, the dominant mechanism is known as the Froelich interaction.
The Froelich interaction, okay.
This is the strong coupling between the charge carrier and the macroscopic electric field generated by longitudinal optical phonons, the LO-phonons.
Ah, the LO-phonons.
Yeah.
Because their out-of-phase motion creates significant polarization.
Precisely. Significant polarization that interacts strongly with electrons.
For those of you who appreciate the elegance of physics, this whole process is formally captured in a quantum mechanical Hamiltonian, which has terms for the electrons, the phonons, and crucially, an interaction term.
The Heath term.
Right. This interaction term fundamentally describes how an electron changes its state by either emitting or absorbing a phonon. And the probability of the scattering is governed by something called the electron-phonon coupling matrix element. Sounds complex.
It can be, but for the specific case of the Froelich interaction with LO-phonons, this complex interaction can be beautifully simplified into a single dimensionless parameter. The Froelich coupling constant, alpha.
Alpha, a single number.
A single number. And what's remarkable is how this single alpha value tells us so much. It connects the microscopic quantum interaction strength to several fundamental and very measurable properties of the material.
That's fascinating. So let me see if I get this. If I have a material with a larger band, the effective mass, that would mean a larger alpha, because a slower electron would hang around the ions longer, leading to a stronger, more prolonged interaction.
Exactly. You nailed it. And similarly, a lower LO-phonon frequency, sometimes called a soft lattice,
Okay.
indicates it's easily deformed, also boosting that coupling and increasing alpha.
So it's like a really responsive dance partner in a soft environment makes for stronger coupling. Makes sense.
Yeah.
And the formula also involves the static and optical dielectric constants. How do those play into it?
That's the subtle but really powerful part. The difference between their inverses, it precisely quantifies the ionic contribution to screening. E includes screening from both electrons and ions moving. E-ether only includes electrons because the ions are too slow to respond to high-frequency light, so the difference isolates the screening that comes purely from the ions displacing.
Which is exactly what optical phonons are.
Precisely. So we're connecting the strength of a fundamental quantum interaction and, by extension, the degree of mass enhancement to bulk, classical properties like dielectric constants that we can actually measure in the lab.
That sounds like an incredibly powerful tool for discovering or designing new materials. And based on alpha, we define coupling regimes, right? Weak, intermediate, strong.
That's right. Weak is typically alpha less than about 1. Intermediate is roughly between 1 and 6. And strong coupling is alpha greater than 6.
So for instance, in a common semiconductor like GAs, alpha is tiny, like 0.07 weak coupling.
Very weak.
But in promising materials like these metal halide perovskites, alpha can be between 1.7 and 2.2. That's firmly in the intermediate coupling regime, where these Polaron effects must be quite significant.
Absolutely significant. But it's important to remember, EPC isn't necessarily a universal constant even for a given material. It can vary with conditions.
Oh, like what?
Well, temperature, for one. It can increase, decrease, or even show non-monotonic behavior depending on the details of the material's electronic structure near the Fermi level.
Okay.
It also varies with the electron's energy. For example, in a topological insulator like by Euros, the coupling is actually strongest near the special Dirac point and then weakens at higher energies.
Interesting. And different phonon modes matter too.
Hugely. Different phonon modes can couple with vastly different strengths. In CSP-BBRI, for instance, specific lead-bromine stretching modes couple to electrons about 2 orders of magnitude stronger than other phonon modes.
Wow, 100 times stronger.
Yeah. So this means that certain specific lattice vibrations can truly dominate a material's electronic properties. It's not just about the overall material, but the specific ways it vibrates.
So with this electron-phonon coupling firmly established, the electron is no longer just a Bloch electron. It's transformed into something new, the Polaron. This is that composite quasiparticle consisting of the charge carrier, the electron or hole, plus the cloud of virtual phonons it dynamically creates and drags along as it moves through the crystal.
It's a great way to put it. Imagine the electron's electric field polarizing the surrounding dielectric, displacing the ions. This displacement creates a potential well that then acts back on the electron, effectively self-trapping it, at least partially.
So it digs its own little hole and sits in it.
Kind of.
Yeah.
And this combined entity, the electron intimately coupled to its accompanying lattice deformation, propagates as a single coherent unit. It is, in essence, the true charge carrier in these polar materials.
And the formation of this polaron has 2 key inseparable consequences. First, its total energy is lower than that of the non-interacting electron. It's more stable because it's sitting in its own self-induced potential well. That's the self-energy part.
Right, stabilization.
Second, and this is the crucial part for our deep dive, the polaron is simply more inert. An external force now has to accelerate not just the electron, but also this co-moving cloud of lattice distortion. It's got more baggage.
Exactly. This added inertia manifests as an increase in its effective mass, giving us the Polaron effective mass, cool.
Okay, pull.
And the degree of this mass enhancement directly depends on our Fruelich coupling constant, alpha.
Right. So how does that scale?
In the weak coupling limit, where alpha is much less than 1, the mass enhancement is slight. It's approximately in pole n times 1 plus alpha 6, just a little heavier.
Okay, small correction.
But in the strong coupling limit, alpha much greater than 1, the increase is dramatic and non-perturbative. In pole scale, something like alpha to the power of 4 times mm.
Alpha to the 4th power. Wow, that could get huge.
It can get very large. And for all coupling strengths, there are theoretical models, like the Feynman Polaron model, which are highly accurate.
So it's not just a subtle effect then. It's a measurable additive increase to the electron's mass, even in that intermediate coupling regime you mentioned for CSB-Brin.
Definitely. In CSB-Bras, the bare band mass is about 0.17 times the free electron mass, and alpha is around 1.81. The Feynman model predicts a renormalized Polaron mass of about 0.24 times the free electron mass.
That's a noticeable increase, like what, 40, 50% heavier?
Roughly, yeah. It's significant.
And here's a crucial distinction you mentioned. Not all polarons are created equal. We classify them into large or Fruelich polarons and small or Holstein polarons.
That's a really key distinction.
This distinction isn't just about size, is it? It fundamentally dictates their transport mechanism.
Exactly. It's about how they move.
So is it like the difference between someone carrying a small, light backpack versus someone dragging a huge, heavy wagon affects how fast they can go and how they move?
That's a pretty good analogy. Large polarons, the Fruelich type, form when the coupling is weak to intermediate, so alpha less than about 6. The electron's wave function and its accompanying lattice distortion are delocalized, extending over many unit cells. You can think of it like a heavier Bloch electron.
Still wave-like.
Still wave-like, yeah. It moves via coherent band-like motion, and its mobility generally decreases with increasing temperature because there are more phonons around to scatter it.
Makes sense. These are common in conventional semiconductors like GIs and in perovskites.
That's right.
And the small polarons then, the Holstein type.
In contrast, small polarons form in the strong coupling regime, alpha greater than 6. Here, the electron becomes strongly self-trapped, localized to roughly 1 unit cell. The potential well is very deep.
Wow, really pinned down.
Yeah. And the transport mechanism shifts dramatically. It goes from coherent band motion to incoherent, thermally activated hopping between adjacent sites.
Hopping, like jumping.
Literally needs thermal energy, heat, to help it jump over the potential barrier to the next site. Consequently, their mobilities are extremely low, often less than 1 centimeter AVS.
That's really low.
Tiny. And unlike large polarons, their mobility actually increases with rising temperature because more thermal energy means more hopping.
That's completely the opposite behavior.
It is.
That's a profound physical dichotomy. This transition from large to small polarons is not just a quantitative difference in mass or size, it's a fundamental qualitative change in the nature of the charge carrier. It's a type of localization transition, where the particle's own interaction with its environment basically causes it to get stuck.
That's a perfect summary. It's a self-localization phenomenon.
Now, theories are great, and we've built a pretty compelling picture so far, but in physics, seeing is believing. How do we, as physicists, move beyond the theoretical elegance and actually prove this isn't just a mathematical construct? What experiments confirm this invisible weight?
That's the beauty of it. We have incredibly sophisticated experimental techniques that directly probe these properties. One of the most direct and accurate methods for measuring effective mass is cyclotron resonance.
Cyclotron resonance. Okay, how does that work again?
You apply a static magnetic field, B. Charge carriers inside the material are forced into circular orbits. They orbit at a specific frequency, the cyclotron frequency, which is S equal EBM. It depends directly on the mass.
Okay, frequency depends on mass.
Right. Then you shine microwave or far infrared radiation on the sample. If the frequency of this radiation matches the cyclotron frequency, the carriers resonantly absorb the energy. You see a peak in absorption. By finding the frequency of that peak, you can precisely determine the effective mass.
Simple in principle. And in polar materials where electron-phonon coupling is strong, I'm guessing the mass measured by cyclotron resonance isn't the bare band mass.
Exactly. It's the heavier Polaron effective mass, impol.
Direct measurement.
Absolutely. In fact, some of the earliest evidence for polarons came from these measurements on materials like cuprous oxide, Kiro, way back. The carrier masses they measured were significantly heavier than predicted by simple band theory alone.
Okay, but is there like a smoking gun, something even more definitive?
There is. The most dramatic signature is the resonant magnetopolaron effect. This is really cool.
Okay.
This occurs when you tune the magnetic field so that the cyclotron energy of the electron, that's UC, precisely matches the energy of an LO-phonon, HO.
So the orbiting frequency matches the vibration frequency energetically.
Exactly. At this exact resonance, the strong electron-phonon coupling causes the single cyclotron absorption peak to split into two distinct branches. It's a phenomenon called level anticrossing.
Anticrossing. Okay.
This splitting is an unambiguous fingerprint of the electron's interaction with that specific LO-phonon mode. And the size of the splitting tells you directly about the coupling strength, alpha. It's incredibly powerful evidence.
Wow. Beyond just mass, though, can we actually see the electronic band structure of a material directly? I know there's a technique for that.
Angle-resolved photoemission spectroscopy, or ARPS?
Yes, right. High-energy photons knock electrons out of the sample.
Exactly. And by measuring their kinetic energy and the angle at which they fly out, scientists can reconstruct their original energy and momentum inside the crystal. Basically, you map out the E versus K relationship, the band structure.
So what exactly does ARPS reveal about polarons? Does it see the bare electron or the dressed one?
It sees the physically real dressed bands, not the idealized bare bands you might calculate with standard density functional theory that often neglects or approximates EPC. ARPS measures what's actually there.
Okay. And what are the signs of polarons in the ARPS data?
The signatures are quite clear, actually. First, you see band flattening. Energy bands near the Fermi level appear flatter than the bare band theory predicts.
Flatter, meaning heavier mass.
Precisely.
Yeah.
Since effective mass is inversely proportional to band curvature, the second derivative of E with respect to K, this flattening is direct visual confirmation of mass enhancement. You literally see the heavier mass in the band shape.
That's amazing. And then there are kinks. I've heard about those.
Exactly. Kinks are another key signature. You see a sharp change in the slope or the velocity of the measured band. This kink appears at a specific binding energy below the Fermi level.
And that energy corresponds to?
It corresponds to the characteristic phonon energy, like Shulo for LO-phonons. This kink literally marks the energy threshold where electrons can efficiently couple to and emit those specific phonons. It's like a marker saying phonon interaction happens strongly here.
So ARPS provides both the mass enhancement via flattening and the energy scale of the interaction via kinks.
Yeah.
That's pretty robust quantitative evidence.
It really is. And we see this clearly in materials. For example, let's go back to CSP Bros.
Yeah.
Ab initio calculations, the Baer theory, predict a whole effective mass of about 0.17 times the free electron mass.
Okay, 0.17 bare.
But high-resolution RP's experiments directly measure a significantly heavier Polaron mass of 0.26 plus or minus 0.02 times the free electron mass.
So 0.26 measured, that's that 50% enhancement again.
Exactly. And this experimental finding aligns beautifully with the theoretical predictions from the Feynman Polaron model using the known alpha value. That model calculates 0.24.
Wow. 0.26 measured, 0.24 predicted. That's a remarkable agreement, almost eerily accurate.
It shows the power of both the theory and the experiment. What's even more fascinating, though, is how seemingly contradictory results from different experimental probes can sometimes deepen our understanding, not confuse things.
Oh, how so?
Well, sometimes magneto-optical studies done in low magnetic fields show a larger effective mass than similar studies done in very high magnetic fields.
Wait, why would the magnetic field strength make a difference to the measured mass? That sounds like a paradox.
Yeah.
How can the mass depend on the measurement condition?
It's not really a paradox. It's all about timescale. It's a beautiful confirmation of the Polaron's dynamic nature.
Time scale. Okay, explain.
In low magnetic fields, the electron's cyclotron frequency, Bach, is slow compared to the phonon frequency, OLO. This allows the massive ions in the lattice ample time to fully respond and form a complete polarization cloud around the orbiting electron.
So the electron drags its full phonon baggage around.
Exactly. So the experiment measures the fully dressed Polaron mass, Phonons.
Okay, low field, full Polaron mass. What about high field?
In very high fields, the electron orbits so rapidly, suck can become much larger than a fellow, that the heavy ions simply cannot keep up. They're too sluggish to follow the electron's fast motion.
The electron outruns its own distortion.
Essentially, yes. The phonon dressing is effectively stripped away, and the experiment probes something much closer to the bare Bloch electron mass.
That's incredible. So the dependence on the probe's timescale, set by the magnetic field here, beautifully confirms the Polaron's composite dynamic nature. It's not just a static, heavier particle.
Precisely. It highlights that the dressing takes time to form.
Okay, this invisible weight isn't just a fascinating quantum phenomenon. It clearly has profound macroscopic consequences for materials. The most immediate impact, I imagine, is on electronic transport, right? Conductivity.
Absolutely.
A larger Polaron mass, skim-pol, directly increases the carrier's inertia. It's harder to accelerate in an electric field,
Yeah.
which means lower mobility, back to Sampopelli, and thus lower electrical conductivity.
You got it. That's the most direct effect. And beyond just inertia, the electron-phonon interaction itself is a primary source of scattering, especially at higher temperatures, which further limits mobility by reducing the scattering time.
So it hits mobility in two ways, heavier mass and more scattering.
Right. Polaron formation is often doubly detrimental to conventional conductivity. This is why many materials with strong EPC, think of many transition metal oxides, are often electrical insulators or poor semiconductors. Their charge carriers might be present, but they're sluggish, forming heavy polarons that don't move easily.
And the type of polaron dictates the transport mechanism, as you said.
Mhm.
Large polarons move by coherent band transport. Mobility decreases as temperature goes up because of more scattering. But small polarons, being self-trapped, move by that incoherent hopping, a process that actually increases with rising temperature because they need the heat to jump.
Correct.
And their mobilities are also incredibly low, you said, often less than 1 centimeter jumpets.
Yeah, very low compared to band transport.
However, you hinted that polaron formation isn't always a bad thing. There was this polaronic protection.
Yes. It's quite intriguing. In certain soft, ionically bonded systems, like those halide perovskates we mentioned.
The solar cell materials.
Exactly. The phonon cloud that forms the polaron can effectively shield the charge carrier from scattering off other things, like charge defects or even other carriers.
So the baggage protects it.
In a way, yes. This polaronic protection can lead to surprisingly long charge carrier lifetimes and diffusion length, even in materials that aren't perfectly ordered. And those long lifetimes are highly desirable for applications like solar cells and LEDs. So sometimes a little extra baggage is actually a good thing.
I love that idea of polaronic protection. Nature finds a way. You can also see the fingerprints of polaron formation in optical spectroscopy, right? Like how the material interacts with light.
Definitely. Using techniques like infrared spectroscopy, you can measure the frequency-dependent optical conductivity.
And what do you see?
Well, instead of the typical Drude peak you'd expect at low frequencies in a simple metal or semiconductor, which signifies free carrier absorption.
Right, the standard response.
Materials with strong EPC often show a significant shift of oscillator strength. The Drude peak gets suppressed, and a new broad absorption band appears in the mid-infrared range.
Mid-infrared, so not free carriers absorbing. What is it?
It's often interpreted as the Polaron absorption peak. It corresponds to the photoexcitation of the electron from its ground state within the Polaron potential, well, to some higher excited state, still bound within that potential. It's not simple free carrier absorption.
Not exciting the Polaron itself.
Exactly. So this broad mid-infrared absorption, coupled with a suppressed low-frequency Drude response, is a classic optical fingerprint of Polarons. It's been extensively studied in materials like strontium titanate, SRTO.
Okay, but perhaps the most profound and, frankly, paradoxical consequence of electron-phonon coupling lies in the phenomenon of conventional superconductivity.
Ah, yes, the big one.
The very interaction that makes polarons heavy and causes electrical resistance in the normal state is also the essential pairing mechanism that enables perfect dissipationless current flow below a critical temperature.
It's truly one of the most beautiful and counterintuitive aspects of condensed matter physics.
It really is a paradox.
Mm.
Electron-phonon coupling is simultaneously the source of resistance for individual charge carriers and the origin of perfect conductivity for paired carriers. How can that be?
It really is mind-bending. It's one of those elegant ironies in physics that still makes you scratch your head a bit. You'd think the thing making it harder for one electron to move would be the last thing you'd want for perfect conductivity for two, but here we are.
So break it down. Single particle view versus two particle view.
Okay. From a single particle perspective, as we've discussed, an electron moving through the lattice gets bogged down by interacting with phonons. It creates that distortion, forms a heavy polaron, and gets scattered. That leads to resistance. Simple enough.
Right, resistance. Bad for conductivity.
But now consider two electrons. From a two-particle perspective, a different story emerges.
Okay, what happens with two?
So if I visualize it, the first electron moves through the lattice. As it goes, its negative charge attracts the positive ions towards its path. This creates a transient region of slightly excess positive charge behind it, kind of like a tiny positive wake made of virtual phonons that lingers for a very short time.
A positive wake. Okay.
And then a second electron, maybe trailing the first one slightly, comes along. What does it see? It sees that transient positive region left by the first electron.
And electrons are attracted to positive charge.
Exactly. So this phonon-mediated attraction, this attraction to the positive wake, can actually overcome the direct Coulomb repulsion between the two negatively charged electrons.
The phonon acts like a mediator, creating an effective attraction.
Precisely. It binds them into a weakly bound pair called a Cooper pair.
The Cooper pair, the heart of conventional superconductivity.
Absolutely. And these Cooper pairs, being composed of two fermions, behave like bosons.
And bosons can do something electrons can't.
They can all occupy the same quantum state. They condense into a single macroscopic quantum state. This condensate can then move coherently through the lattice without scattering off imperfections or phonons in the same way individual electrons do.
Resulting in zero electrical resistance. Superconductivity.
Exactly. And the strength of this electron-phonon coupling, the same alpha that determines our Polaron mass enhancement, also dictates a binding energy of these Cooper pairs and, consequently, the superconducting transition temperature, Tc. It's an incredible balancing act in nature. Stronger coupling generally means heavier polarons, but also stronger pairing and higher Tc up to a point.
Wow. Okay, this deep dive has really shown us that the influence of phonons on an electron's mass in a crystalline solid is, well, it's a cornerstone concept in condensed matter physics.
Absolutely fundamental.
It's a profound example of mass renormalization, where the bare charge carrier, which is already a Bloch electron dressed by the static lattice,
The first dressing.
is further dressed by its dynamic interaction with lattice vibrations, the phonons.
The second dressing, leading to the Polaron. This core mechanism, electron-phonon coupling, gives rise to this physically real, heavier, and more inert quasiparticle.
And we've seen how its mass enhancement isn't just theory. It's been unambiguously observed and quantified by techniques like RPs, which literally visualizes the flattening of electronic bands,
And those characteristic kinks.
and cyclotron resonance, including the resonant magnetopolaron effect, which directly measures the increased inertial mass and the coupling strength.
The experimental evidence is really solid.
And the consequences of this phonon-induced mass renormalization are just incredibly far-reaching. It limits conductivity in many materials, creates unique optical signatures, dictates transport mechanisms.
And most remarkably, it enables the amazing phenomenon of conventional superconductivity through Cooper pairing. That duality is just fascinating.
It really is. So what does this all mean for you, our listener? Consider the intricate dance happening right now within every electronic device you own. The weight of the charge carriers carrying signals and energy isn't fixed like a textbook constant.
Not at all.
It's dynamically sculpted by these atomic vibrations, these phonons. This deep dive shows us that controlling this invisible, fluctuating mass, perhaps by engineering materials at the atomic level, to tune that electron-phonon coupling.
Yeah, material design.
That could be the key to unlocking the next generation of technologies. Think better solar cells, more efficient thermoelectrics that turn waste heat into electricity, maybe even components for quantum computers.
Or the ultimate goal for many, entirely new forms of superconductivity, maybe even pushing towards room temperature.
Exactly. The future of material science might just depend on how well we can learn to choreograph this microscopic ballet of electrons and phonons.
Oh, something to think about.